Good morning, everyone. Welcome back to the course PH8253 Physics for Electronics Engineering. We are discussing Unit 3 Magnetic and Dielectric Properties of Material. In today's class, we will be discussing about ferromagnetism, domain theory. In previous class, we have seen that ferromagnets exhibit large values of susceptibility and relative permeability. These large positive values can be attributed to the fact that ferromagnetic material have regions within the material. Let us consider a sample as shown. Let us assume there are three regions within this sample, and the dipoles, that is the atomic dipoles within these regions, are such that they are aligned with each other. This mutual spin alignment of the atomic dipoles can be attributed to the fact that there is coupling interaction between the dipoles which make them mutually aligned. So the presence of these regions, which are called domains, is what is responsible for the large and positive magnetization. In addition, the permanent magnetization of ferromagnetic material. If we assume that this is region 1, this is 2, and this is domain 3, and if M1 is the net magnetization of region 1, M2 the magnetization of region 2, and M3 the magnetization of region 3, the net magnetization would be the weighted average. V1 is the volume of region 1, 1 by V, where V is the sum of the three volumes, V1, V2 and V3 respectively. So the net magnetization would be the weighted average of the magnetization of different domains. For a specimen that has been left out for a long time, for a specimen that has not been subjected to an external magnetic field, the net magnetization is zero. That is, the domains are such that the average energy is least in the absence of external magnetic field. This ensures the stability of the ferromagnetic material. That is, when H is 0, M is also, the net magnetization is also 0. So in ferromagnetic material, the uncancelled spin magnetic moments result in the atomic magnetic moment. In addition, there is also a small component of orbital magnetic moment. Coupling interaction between the spin magnetic moments of adjacent atoms result in alignment of one another. So coupling interaction is responsible for formation of domains. That is regions within the magnetic material where adjacent atomic dipoles are aligned along the same direction. So domains are large volumes of space within the material where there is mutual spin alignment. The spin alignment is due to coupling interaction. Direction, as can be seen from this figure, the direction of alignment and magnetization vary from one domain to another, and the net magnetization is the weighted average. When we consider this figure, we have this region separating the domains, which is the domain wall. It is also known as the block wall or domain boundary. It is not a single line or a single atom that separates the domain. It extends over a region of space. So if I were to visualize the domain wall, I have two domains such that the spin alignment in this domain is in this direction, and here it is pointed downward. There is not an abrupt change from this domain to the other. The change in the direction of the dipole happens gradually within the domain wall. Change in the dipole moment happens gradually within the domain wall. There are various energies associated with the formation of domains, and these are responsible for the strong magnetization observed in case of ferromagnetic material. So, the energies associated with domain formation can be listed as exchange energy, the exchange energy is the energy that is responsible for the mutual spin alignment of the magnetic moments without violating the Pauli's exclusion principle. The magnetostatic energy is high when the alignment increases. It is high at the surfaces. Anisotropy energy. Energy required for magnetizing a specimen is found to be different along different planes. For BCC iron, the 100 plane exhibits a higher magnetization for the same applied field, whereas for nickel, the 111 plane shows a higher magnetization compared to other directions for the same applied field. Excess energy required to magnetize a specimen along a particular direction is known as anisotropy energy. So the domain wall energy. So domain wall energy is the energy associated with the formation of domains. It is the domain wall energy is such that exchange energy and anisotropy energy have optimal values. But the net energy of the specimen is low. Magnetostrictive energy. This the change in dimensions when a specimen is taken through a cycle of mag- magnetization. This is called magnetoelastic behavior. The formation of domains and their volume depends on all these five types of energy, and when a ferromagnetic specimen is subjected to an external magnetic field H, if we consider a specimen having four domains, and if the field is applied in this direction, when H is 0, the net magnetization is also 0. But as H field increases, this point, the domains get oriented such that the favorable ones grow at the expense of the unfavorably oriented domains. That is, there is movement of domain walls such that The unfavorably oriented domains become smaller, whereas the atomic dipoles get oriented favorably, that is in the direction of the applied field. So as H increases, this is what happens. So for a further increase in H, the entire specimen becomes a single domain, and saturation magnetization is achieved. Saturation magnetization MS is achieved when a whole specimen becomes a single domain and all the dipoles are oriented in the field direction. So this is how the ferromagnetic specimen becomes a single domain on application of the external field. The saturation magnetization is temperature dependent. As temperature increases, the coupling interaction decreases. Hence, the saturation magnetization MS decreases with increase in temperature. The magnetic susceptibility chi of a ferromagnetic material is given as C by T minus Tc. The Tc is the Curie temperature. It is the temperature at which the coupling interaction is completely destroyed. That is, the ferromagnetic material becomes paramagnetic. Curie temperature of few ferromagnetic materials are listed as shown. For ferrous, it is 768 degrees Celsius. For cobalt, the Curie temperature is 1120 degrees Celsius. For nickel, it is 335 degrees Celsius. And for Fe2O3, the Curie temperature is 585 degrees Celsius. The 1 by chi versus T graph for a ferromagnetic specimen looks like this. Susceptibility becomes 0 at T equal to Tc. Above the Curie temperature, the ferromagnetic material behaves as paramagnetic. This is known as Curie-Weis's law. In this expression, chi equal to C by T minus Tc, C is a constant. Let us take a look at whatever has been discussed in today's class. We have discussed the ferromagnetic domain theory. We have seen that domains are large regions within the volume of a ferromagnetic specimen where there is mutual spin alignment due to coupling interaction. Uncancelled spin of the electrons with a small orbital contribution result in a net magnetic moment of that atoms. The atomic dipoles get aligned due to the coupling interaction. The absence of external field, the net magnetization for a ferromagnetic specimen is zero. This can be attributed to the fact that the domains are oriented such that their net magnetization cancel each other. As the field increases, the domains that are favorable to the external field grow at the expense of unfavorably oriented domains until the entire specimen becomes a single domain and net magnetization is in the direction of the external applied field. Since the component due to the net magnetization is very high, the expression H B equal to mu naught H plus mu naught M gets modified as B is approximately equal to mu naught ms saturation magnetization. Saturation magnetic induction is equal to, because this is very small compared to the contribution due to the dipoles. Hence, the susceptibility of a ferromagnetic material is temperature dependent, and as temperature increases, the saturation magnetization decreases because increase in temperature increases thermal vibration, destroying the coupling interaction. 1 by susceptibility versus absolute temperature curve shows that susceptibility becomes zero at the Curie temperature. Curie temperature for few material is listed here. The formation of domains is such that the energies associated with the domains are the least. In the next class, we will discuss about hysteresis. Thank you for